Welcome everyone to this second video about OCaml, and my name is David Broman, and I'm going to give you some advice on how to get started with the programming in a typed functional language in general, but in particular in OCaml. And if you haven't watched the first video, it might be good to do that as a starter if you are new to this. Right, so what we are going to do today is to learn about functions and how you define some basic functions and what also types and type inference actually means in OCaml. And functions is, of course, really the core of a functional programming language, right? So we saw in the first video how to invoke a function, so some standard library function, but now we're going to create some functions. So let's get started. Let's create a function called double. And then we do like this. So what you can see here is that we use the let keyword here as well. In the first video, we just showed that you can use lets to define a name, but you can also define a function directly here. So now we define a function double, which has one parameter, x. And this is the body of the function, which is always an expression. And it's just adding together it 2 times. So here is the function. What we can see here now is that it evaluated this, and then it just defined this function, and it also shows the type. So you see here that double has got the type integer to integer. So what this means is that to the left here, it's the type of the parameter, which is an integer. It takes x here, and it returns an integer, which is the result of evaluating this expression. And this function type or arrow type is shown with this kind of arrow style. Right, so this is a basic function, and then we can call it double 5, 6, and we get 12, or 10, we get 20. Right, so it's you invoke the function using, again, juxtaposition. So you do not write like this, which will you write like in another language, but you just type space and then the argument. Let's go back to the editor again and define another function here. Let's call it foo, as this is common. And here you can see that you can have many parameters. Like now I have 2 parameters, x and y, and then I type in some expression. Like in the last lecture, we learned about if expressions. Let's do an if expression. So if is larger than y, then let's do, for example, x1 times 100, else we return y. We take the two parameters x and y. The if expression here, this whole thing here is evaluated into value, which is then returned. We know that the return value needs to have the same type. So here we can see that this is an integer and this is an integer. And we select this based on this expression here, is x larger than y. We can check it, but we don't have to do it. We can just evaluate it. And then we get the result. And there we can see here directly that the type the type of the function is int to int to int. So how did we didn't express that, right? And that is because OCaml's got type inference, which means that you do not have to give the types explicitly here at the functional level, but the type system will infer it. So it figures out that that x must be an integer and y must be an integer because of how it's used. And if you do it in the wrong way, you will get a type error. Right, again, we saw here that we see here how this arrow type is used. And now you see that you have int to an int to an int. And how do you read that? Well, you read that by looking at that. You see here that there are 2 arguments or 2 parameters, x and y, and this is the same in the matching. You read it in the same direction, that x here corresponds to this int, y here corresponds to this int, and the last int is the result. So this is how you read the signature of the function, the type signature. So we can then call foo, let's say 7 and 10. So you see that 7 it's not larger than 10. So then it should actually return the y, which returns then 10. Right? Now it is actually so that you don't have to supply all the arguments directly. And this is one of the key features in functional programming and like in OCaml, and this is called currying. So this means that you can apply just the first argument and then get what is called a closure back. So if we now call foo and 7, what is returned is really a function. So you see that we applied the first argument here, and that what we get back is the rest. And that is, so you get a function back that now just takes 2 arguments. So if we do this again, but we give it a new name, let's call it a bar here, or just foo2. Let's call it foo2. Now we have foo2 takes an integer to an integer, and then we can then apply it again. So we can call foo2 with 10, for example. So what happens is that when you invoked foo with 7 here, the 7 is kind of stored inside foo2, which is also a value. So it remembers that you have applied this argument. And this is what is called a closure, where the expression is remembered inside the expression. It actually keeps the environment of what was going on when you invoked the function. And then you have this, and then you can apply it later on. And you can apply foo2 with two different values as well, like 3 here. And now, since 7 is larger than 3, we got into this branch and we multiplied the first one, the x, with 100 and got 700. And this you could do the double function as well. If we look at the double function we defined before, we'd never defined it before. We can just define it again. And then this, right? Then you can define, also just call that with 1 argument. And it is what actually 1 argument. So if you try to do it twice with double, what happens then? Double 8, 10. You get an error. Why do we get an error here? Well, it's because double, if you just invoke it once with this one, you get an integer, and you cannot apply an integer to an integer. So this double function only had 1 parameter. So when you have applied the first argument, you have already done all the work. And that's why it says that this part here, double here, it is not a function. Okay. Let's go to another example. We can clear this out and then go to the editor. Let's define another function. Let bar S1, S2, both. Okay, so we define now that we have a function bar that has 3 arguments, S1, S2, and both. And let's do a if expression, both. So we check here if this is true or not. So by just typing this, the type inference will understand that both needs to be a Boolean, because we used in the context where it's only Booleans are allowed. And then let's say that we do a string.length. So we suppose, I mean, it assumes that it will be a string that comes in here, and we do S1, S2. So we concatenate these 2 together. And since this operator assumes that the operands are strings, the type checker can infer and say that, oh, this one and this one needs to be strings. else, and as you see here now, this string.length, it returns an integer. So the else branch must also be an integer, and just say that we return like this. Let's evaluate this one. And what we can see here now is that we have three arguments, or three parameters, S1, S2, and both. And this is the type signature. And you can see that you have three arguments here as well in the type: string, string, bool, and then it returns an integer. So we see that S1 matches to this string, S2 matches to that it's a string, both is a Boolean, and it should return an integer. And then we can just run that one, bar I there, and then say true here, and it's then evaluates, concatenates these two strings and checks and see how the length of it, and sees that it's 7, right? And we could of course, as I showed you before, let let's just call it f, a new function, and then we call bar and then high, and let's say that we don't do anything more, or maybe you do there. Now we have applied two arguments, string and string, high there. So what we get back is a function that only takes the Boolean and the integer, and then we can run that f with true. So then it uses these, it remembers these strings inside this closure, this f, which is now a closure, which is a function. And you can just call that, and we can, with a different argument, and we can call it with false here, and then it will run this if expression and evaluate and use the else branch instead. Right. So you see here how you can invoke the functions over and over again, and also how you can partially apply the different arguments. Right, so we have now defined functions using names, but it's also possible to have anonymous functions, and this are called in theory we talk about lambdas. So you define a lambda in OCaml by using the fun keyword, just because it's fun, or maybe it stands for that it's a shorthand for function, and function might be too long to type, so then someone decided to just call the keyword fun. So let's define functions where you have x as a parameter. So you write the parameter there, and then what comes after this arrow is the expression. So here, this is a function, goes from int to int, right? X int to int. So we can actually apply that directly. We can do like this, and then run it. So then we have a function here, and then we apply the function and we get a result. We can also, instead of applying it directly, we might want to give it a name. Let's give it a name. Let f equals the function. Then we are actually giving this a name, and we can use it again. Right? Okay, so we see here that this is basically the same thing as we did before, but if lambda is just a function that does not have a name that we then later can give a name. And we can use this in a lot of different settings. You'll see later on in examples how we will use it. But let's now look at just another example. We can write like this: fun x, and then we can write fun again, y, x plus y. So what happens here is that this is a function, and this function contains another function. And then you see that x and y are then available here in this body. So if we evaluate that, we see that we get back is a function that takes two arguments, x and y, and they return an integer. So you see that there is really a matching between this, how we define a lambda and the types. And if we just apply it with one value, surprise, we get a closure back where we have applied one argument, the x here. So you can think about it as this 8 is substituted for the x and put there. And then this function here is removed. So you could just have this function left, where this is an 8. And this is the function then that we are returning. And if we do like this, we apply it directly. We get 18. Let's go to the editor again here, and we can clear it out. And then we write here a few expressions here. Foo1 x y equals to x plus y. Let foo2 be a function, so a lambda, and fun y, lambda x plus y. And finally, write foo3 equals to fun x y. So now the question is for you, and you can pause the video and think a little bit first, but the question is are these functions the same, or are there any semantic differences? Meaning, is there a meaning difference between the different types? Okay, so let's pause the video and think a little bit, and then come back. And now you're back, and the answer is there is no difference. These expressions are all the same semantically. It's just different ways of typing it. So you can actually think that this foo2, where you have embedded lambdas, that's everything that you do in a function language. You always have these lambdas. You have a lambda encapsulated in the different lambda. This foo1 is just a syntactic sugar. So you can see it, it's a little bit easier to write it like this, but it is actually 2 nested lambdas that are defined here. And the third thing here is just a way, also another syntactic sugar. So when you define an anonymous function, you don't have to write like fun nested in funs, but you can write the arguments directly in OCaml. But again, it is actually 2 nested lambdas. So if you evaluate this, you will see that you get the same signature for all of them, and you can play around and try out and see that they are behaving exactly the same. Right. And the next thing we want to show here is a little bit more advanced functions. So we have just shown here very simple functions that evaluate a value, but typically when you want to write some real programs, you need to have some sort of recursion to be able to write some interesting programs. So let's type in here a little bit more interesting program here. So let rec. So this is when you define a recursive function, a function that is calling itself, you need to use this rec keyword here. So let's call it prn, string, and end. So now we see that we have a function called prn, and it's got 2 arguments. And let's start with an if expression and say that if n is not equal to 0, then this means that we will do something as long as n is not 0. So we will actually count down and do something for an n number of times, and then do this until it reaches 0. So as long as it's not 0 now, then we will print. This println line prints some string, and then also adds a new line, and we'll print string. So now the type checker understands that, oh, string needs to be a string. And then we have this. This is a sequencing operator. So it says that if you have something that ends with what's called the unit type, basically do nothing, then you can do this and then have another expression that is evaluated after this. And unit types are used when you have some sort of side effect. So printing is an example of a side effect. Something happens as a side of the function. And in this case, it prints to the standard output. And then you have this prn string n minus 1. And let's see here, and then we can do this, and then else. And here in the end, this last part here, we are evaluating and saying that if it has reached 0, so then if it's reached 0, then it will return the unit type. So this is the value for a unit type, like you write it with parentheses. Just check, see if it works. Yes, and then put it in. Okay. So what happens if we call this one prn high and 3? So what happens is that it's looping. So this is how you write loops in a pure functional way. You do recursion. So here we are calling. We are always supplying the function call here, and we have then the string and the number. And when we enter 3, it will enter here and then print and then call itself, but it will subtract the value with 1 and then call itself. So it will do this 3 times until n here is 0. Then it returns unit, and then it goes back, winds back. So if I will do this again here with 10, I will print high 10 times, right? Okay, and you see here also that this is the unit type, and this is the value. And we can also look at this print end line and just look at the type for that. And you see that print end line takes a string as input and returns the unit type. Right. The next thing to do is for you to write a small function. So now I would like you to write the factorial function. So if you call this factorial function and write like with this, you should return 24, because factorial 24 is actually 1 times 2 times 3 times 4, right? And if you write this, it should return the value of 6, because 1 times 2 times 3 is 6. And please try to do this on your own now, with the knowledge of what you saw in the video so far. And then let's see if you got it to work. And I'll show you a solution directly after. So please pause the video now. And now you might be back. So let's write the factorial function. So again, we need to have a let and rec to do it recursively. We give it a name, fact here, and we have n as the parameter. We want to check now, right? If the value is 0 or 1, because then we should return 1. So if n is less than or equal to 1, then return 1. And as you can see here, you can always split things into separate lines. So you do that in a way that it looks nice, basically. Yeah. Okay. If it's not less than or equal to 1, then what we should do is to recursively call ourselves. So we call fact n minus 1. So we will then decrement n with 1 and call ourselves. And then we multiply by the value n. So that means that the first time, if we call this with 4, it will actually first have 4 here and then call itself. And then when it comes down there, the next level, we will have 3 there and then call itself and so on. So it go down and put everything on the stack, and then it will actually do the multiplications when it comes back. So you're going to get like 4, 3 multiplied by 3, multiplied by 2, multiplied by 1, and you have the result. So we can check the code here. And if we do this, fact 1 becomes 1, fact 2 becomes 2, fact 4 becomes 24. Right. So it seems to work. You have to test it more, of course, to be really sure, but you can trust me on this one. Right. So now let's see if we can create another way of doing this. I mean, this is one way of writing the factorial function, but there is also something that calls match, and that is a match construct that is really, really useful in general, and we'll use it a lot in this course and when you are programming in OCaml. But let's just show how you can use match using the factorial function. So let's again write this fact n, and then we say equals to match n with. So this is match expression says that match the value of this expression with something, and then you write a bar and you say if it matches 0, for example, then return 1. If it matches 1, return 1. If it matches anything else, so this is the wildcard pattern. Do the fact n minus 1, so exactly as we did it above, multiplied by 1. As you can see, these two functions they are doing the same thing. I mean, it's undefined what happens if you supply a negative number, and they will behave a little bit differently then. But let's assume just that this function is defined for positive numbers. Now, if I run this in the evaluator, it will actually define this first and then define this, but the names are shadowed, so it's just the last one that is actually available. So that's why I can run this, and then we'll see that it will first define this one and then define this one. And now if I run fact here, I will execute the last one. So then we can write fact 24 and we get value 24. Okay. So why did I show this? Well, I just wanted to introduce the match statement now for integers. And what it does is that you have patterns to the left and then the results to the right. But in this case, when you do the factorial function, there's no point of using match, right? I mean, this is actually simpler. The difference is that an if expression always have to evaluate into a Boolean, whereas a match, you can match different values using patterns. So for this simple match here, it looks very similar to, say, a switch statement in C, but you will see that matches are much more powerful in OCaml in the end. I also want to show you that you can simplify this a little bit here. So now you see that we wrote this on 2 lines. You can actually put this on the same line. So you don't have to repeat the resulting value if there are several patterns that should result in the same thing. Then you can write like this one or this one, then result in this one. Good. Finally, I would like to show you mutually recursive functions. So we have so far looked at functions that are calling themselves, but sometimes you can have functions that are dependent on other functions, and that function is also dependent on another function. It's not that common that you run into this, but some application really requires it. So I just want to show how you do this in OCaml, and you can look at this as a little bit an advanced topic, and you come back to this when you need it. But I'll show you the kind of the classical example here when you're computing odds and even numbers. So first function we define here is even. So we want to check if return true if the integer numbers is even, so 0, 2, 4, 6, 8, and so on. Then it should return true, otherwise it should return false. So then we say that if n is equal to 0, then true. So if it's 0, it's obviously even, and then we return true. If it's not 0, then we instead call is odd. We should return true if the number is odd, and we subtract by 1. Now we want to define odd. We could do that like let rec here is odd n, and if n is equal to 0, oh, I forgot the equal sign here, n is equal to 0, then false, and false. So if it's 0, it's obviously not odd, so then we return false. Else we return is even n minus 1. Now we say that if this is false, if it's not 0, then we call even. So you see that they will call each other. But the thing is here that when I did this letrec here, this makes it possible for this one to call itself, but it will not be able to call is odd, because is odd is defined below. This is odd can actually refer to is even. So if you try to do this, it will check and say error, and it actually points to this part, and you can actually evaluate the code, and then you see that is odd is unbound, it says. So it doesn't know what is odd. So what you have to do when you have mutually recursive functions in OCaml is to use this and keyword here. So what it says is that this expression, when we jump in, and it will use like, okay, this is also a letrec, but these two are mutually recursive, so they know about each other. And now they can call each other, and we'll see that if we do like this, we get these two functions. And then we can say is even 10 returns true, is even 11 false, is odd 10 false, is odd 11 true. Right. So now I showed you how to define mutually recursive functions as well. So that's it for today. And next up will be that we will look at more immutable lists and polymorphic functions. Okay, thank you for listening.